Okay, so for the last couple of classes, we have been looking at and discussing how to solve some numerical problems in the context of filtration theory. And I left you with some specific constant pressure filtration problem, which also included a scale-up question. So yesterday I gave a hint how to solve it. I suggested that take the geometrical cross-sectional area multiplied by 2 and use that to design the filter press. Why did I suggest that multiplication factor? Because I said that that is the appropriate capital A, the filtration area, to be used in the general filtration equation for dV by d theta, or in the equation for the filtration time, which was the quadratic, assuming the negligible medium resistance. Why did we suggest that? We looked at the equipment. We looked at the way the filter press is set up. We saw how the filter medium actually is hung about a plate and frame assembly. And I said that the rate at which the cake or the biomass accumulates is actually twice that on one side of the frame. That is because the accumulation would take place on both outer or left and right surfaces about the frame on the filter medium. So first, I think you should find the correct filtration area to design this filter. So please see if you can do that. How much does it work out to be? Once you have the effective area, you can multiply it by the thickness of the frame, which was, I think, 2.54 centimeters. Yes, it was. So that gave me 3 into 10 to the power 4 centimeter cube per frame. Then I recommended that you take the density data from the lab scale test and apply that to the scaled up batch of slurry that you have to filter. And find out what is the total volume of the biomass or cake that you have to accumulate. Once you know that, it should be possible for you to design the number of plates and frames. So please see what the total cake volume works out to be. thing is, if you know the total volume of filter cake that you have to process, and since you know using the effective filtration area, how much each frame in terms of volume, I gave you that number, 3 into 10 to the power 4 or so, approximately centimeter cubed. How much frame per frame each frame holds. So you should be able to see that until the frames are totally full, how many you have to give in the design. In other words, how many you must assemble. You should find 9 frames and 9 plates. Okay, so please verify or work out that you get the n equal to 9 for this design. Now you can come to the second part of that question. In that numerical, it was specified that the laboratory scale spherical filter paper of diameter 5 centimeter, it took a long time of 163 minutes. Now, using that 163 minute in the quadratic expression for the filtration time, can you find the filtration constants, that is the specific cake resistance, or rather the specific cake resistance times the viscosity, etc., right? Whatever, because whatever is it will all come as a product form. So see if you can find those lumped parameters. Because once you can find those specific cake resistance into mu upon whatever constant value that you are going to get, you can reapply that quadratic form with a new delta P and a new capital A. That is the scaled up A that you found out in the first part of the problem. And the new delta P after subtracting against the hydrostatic head to which you must raise the water, the filtrate rather. It's given how much the feed pump gives. From that you have to subtract the hydrostatic head to which you have to raise the filtrate. So that will be the new delta P, and you'll use the new A and find out the new time. Yet it is not fully straightforward. There is something you have to work out, you have to think. Because, why is that? Because the way we had derived the expression in the quadratic form, we had the filtrate volume squared in the general equation. First thing here, VE into V, that thing is neglected, so we don't have to worry about the product term, but we have the square of the volume, but the filtrate volume is not given to you directly in the test filtration run. So how will you recast that equation so that you can apply it to the data that is given for the test filtration run. So you really need to think on that. You will have to recast that equation for this particular situation where directly the volumes are not given. So see how you will work that out and how you can apply that equation to this particular situation. The thing is, you are given the filter diameter, so you can find out the area of that spherical filter paper. You are given the delta P. In the test case, you are also given the weight of the crystals. So please use that and rewrite the equation so that you can get mu alpha, the constant unknown, which is the material property. So in other words, instead of using the volume, you have to recast the equation in terms of the weight. Please do work that out and find the new delta P, which will work out to be about 1/4 of an atmosphere after subtraction of the hydrostatic head of filtrate. And now apply that equation a second time with the scaled up area of the large throughput press, plate and frame press with the 9 plates and 9 frame assembly. And find the new time. Of course, you will get a small time because the area is so large. It will be much smaller than what's in the test filtration. Even though the hydrostatic head is somewhat lower. I mean, the pressure drop delta P is lower than in the test case, test filtration case. You ought to get a small time compared to 163 minutes, approximately of the order of 5 to 6 minutes. So check that out. Now, I also gave you a number of other questions. For instance, what will happen if we don't assume incompressibility of the filter cake? Now you will remember we derived the equation both in terms of the filtration equation, both in terms of V plus V equivalent, V plus V effective, which was the fictitious capital VE. But I also showed you that you can derive the same form by the Darcy's law, where the superficial velocity was just k times delta P upon viscosity times L, where k was the permeability constant of Darcy, delta P was the pressure drop, L was the length of the bed or thickness of the cake, and mu was the liquid viscosity. So if we were to integrate that along with the fixed resistance or medium resistance Rm, you would get 1 by A dV by d theta, or 1 by A dV by dt is minus delta P upon mu, and within bracket alpha times W times V by A plus the fixed resistance Rm, right? Now this delta P you replace by the power law, where delta P naught is some constant, true constant, and small s is the exponent, which varies between 0 and 1, with 0 being the incompressible cake limit. Now for any s between 0 and 1, find the new filtration equation, which for this particular way of expressing of the constitutive equation for compressibility will give you an unknown value of s, which has to be found experimentally by the log-log plot of the constitutive equation. You can find by working with that material, small s. I told you that for our yeast samples, it's of the order of s is of the order of 0.3, 0.3. So that has to be given, found experimentally, and then now apply that and get the new equation, which will be valid for a compressible cake also. Then I asked you, how will you set up the problem if I do not want the filtration rates to drop with time, as would happen in the cases we have analyzed so far with the constant delta P? Find out how the delta P should be varied such that the rate of filtration is almost constant. That would be a nice exercise. So now you have to go back to our derivation and redo it for the new conditions. So we don't have to derive every case. So suppose the rate is constant. Find out what the new differential equation would be, and now again see how you're going to linearize that equation and what you're going to plot on the x and the y axis, so that you can get the specific cake resistance times alpha times W, or whatever, by A squared, or whatever is the constant, some function or some product form of lump parameter mu alpha, and how you were going to get the equivalent RM or medium resistance, or in the capital V filtrate equivalent VE, how you're going to find that parameter, how you should plot such that you have a slope intercept form, that is, you linearize that equation for the constant rate and obtain all the parameters. And once you have those parameters, you can find out anything that you want, how much time you need, because you can integrate that again from 0 to t and 0 to v, just as we did, because at time t equal to 0, there was no filtrate volume as per the initial condition. So that is something else that you can work out. Now the number of variants that I can generate over these problems are just so many. There's no end to it. For instance, an interesting question could be, what strategy should I employ? What strategy should I employ, assuming time is fairly long, say of the, I mean, not just that 5 minutes, 6 minutes that we got in that filtration problem, question 1. What strategy should I use? Should I maintain rate of filtration constant? Should I maintain pressure drop constant? Should I maintain something else constant? On what criteria should I do this? That's a harder question. So maybe we didn't reach there. That would be an interesting problem to optimize, you see. It's an optimization problem. We haven't done such problems yet in our course. That is an interesting further advance, which you may even take up in some presentation if you want. I mean, there is no end to the number of innovations that can be done. The problem is, if we maintain pressure drop delta P constant, very soon the cake starts exhibiting higher resistance, so it's not desirable. However, if I have to maintain the rate of filtration constant, that is also problematic, because I have to change, or shall I say increase, delta P in a certain way. So can that be done? That's what has to be figured out. But that depends on the answer to the third question. Maybe a hybrid mode could be adopted, but then we can't adopt them all simultaneously, right? So what should be an appropriate strategy of operation? Harder question. So maybe for the moment, we should limit ourselves to the first 3 questions, which we have been discussing already for the last couple of classes, and not add new ones, because time is coming when we have to close things out. As I said, this filtration design and all. I mean, I'd specialized. I'd done a lot of work on it, though we didn't publish anything on it. But so there's no end to this scale up thing and so on. I had done a design project on it actually. It was submitted to a design competition and it won a prize also for the students. Anyway, those are very long back. There were 3 prizes. It won a 3rd prize. we never understood what was wrong, why, what the first prize design was not shown to us. Otherwise, it would have been interesting for us to look at the first and second prizes. Anyway, it was quite a large problem. We had to draw diagrams. I mean, proper engineering drawings of the design, and a lot of. It was a long, at least 2 month exercise. Anyway, that's 19 a long back problem. So we have to, however, close things, and soon now it's over to all of you, and I will be on the other side of the fence, which will be interesting, more interesting. You can see things from both sides, right? One when you are doing the talking, and the other when you are on the committee, or it's a one-man show here, but all the same, I will be on the other side. So it's over to you, students, which Sarthak will coordinate from 28th, which also happens to be my birthday. So I think there are a large number of scale-up problems in other fields of fluid solid systems, which we haven't tackled. That's one thing that I did not have time for. We had also studied a lot of centrifuge designs. And, we were shocked to find that the scale-up criteria that are often employed are not ideal. And design is still of a very large centrifuge, which can process, let's say, of the order of between 1,000 to 10,000 liters of slurry per hour. It's still not a perfected exercise. So that's something that we will not be able to do, because it is by itself a couple weeks of work. But anyway, so scale up of these devices presents challenges. It's also an interesting question, right? So on these lines, a large number of questions can be asked, and this time we have tried to actually frame some numerical problems, try to actually solve them. You just have to work them out yourself and see that, yeah, it does work out. See, in all of these fluid solid processes, including the one we are studying now, filtration, we are not allowed to increase the pressure drop beyond some level. So that level is generally, we determine it for every system. After that, we do not want any delta P increases. So that is another constraint that is there in actual large scaled up machines, or including the plate and frame press. Ideally, what you have to have is a relatively low pressure at which most of the operation is carried out. And then towards the closing stages, you should be able to increase it, but still keep it below a limit. That will be both safety-wise best and economically also optimal. So it can be proved mathematically, actually. And to that, we have not yet added the cycle, added the washing and the time for a disassembly of the press. So when you do that, because it's not a continuous operation, you see. So to that, when you add the time, you will find the total cycle time, and then you will be able to see what approach is optimal. Anyway, that is sort of beyond our deliberations for the moment. But you get, I mean, when we have to end on some note on things which we haven't done, and which can be, however, discussed in a further version or an advanced version of the course. Okay, I think that's pretty much what it is. And very soon we don't have many more time, much time now. We have to move on to the other last 30% of the course, which is dependent on your group, can have 5, 6, maximum 7 students. Okay. So you can coordinate, somebody can start, and everyone has, we have to do this by 5th of May, right? So we don't have too many classes now. Just 3, I think. Okay, so please coordinate, and it's a job that has to be done, right? We have to mark out of 30. So the minimum is 15. So, you know, and the bar will be every 5 points, right? So that's how I will mark it, and it will be my evaluation. Okay. So good luck on that. You still have time, and coordinate your efforts, and give me a 10 to 12 minute presentation. Starting my birthday next week, next Wednesday. Next Wednesday, correct, yes. All right, thank you very much. Of course, if you have question on these problems, we can spend a few minutes on the 28th. Thanks.